Good morning, everybody. I hope you can hear me okay. Welcome back for the final week of the Summer Intensive Physics 121 Mechanics course. A couple of quick announcements. The last homework is due today at 5 p.m. The final exam for the class is on Thursday. Again, it will run in the 3 hours from 9:30 a.m. to 12:30 p.m. The plan is to break the exam into 3 chunks, one in the first hour, with a break, and then another second hour and a break, and then a third hour. So it'll be a total of 6 questions. It'll be very similar to taking the 3-hour exams one after another. Just so you know what we're doing, today we're going to finish up our discussion of rotation by looking at the gyroscope. We're going to take a look at simple harmonic oscillation, and perhaps if we have time, mop up something having to do with static friction. Tomorrow we'll look at non-inertial reference frames and what this means for the nature of gravity. We'll spend a little bit of time talking about how classic gravity compares to modern gravity, sort of Newton's ideas versus Einstein's ideas. Wednesday, there'll be no new material presented at all, either in video or in the active lecture on Wednesday, but I will review. I'll spend just a little bit of time highlighting what I would call this general strategy for tackling final exams. And then we'll spend the rest of the time with some mix of practice problems and what I'll call clicker problems. You get a chance to vote on your favorite answers and see what makes sense to make sure we're all conceptually pinned down. I have office hours every day this week before the exam. Today's office hours will be at 5:30, but if you need to meet with me before, or if you have some questions, you want to meet some other time, just send me an email and I'm happy to set something up. Let's see, any questions about the logistics of the course? And if you have some and they come up to you, just send me an email. I'm happy to talk to anybody about it. Okay, so what I want to do today, hopefully, so beyond, how can I say, having teach this course remotely at home is mostly feasible and something that we can, it's not as terrible as I would have expected rather, but not being able to directly demonstrate the gyroscope. I mean, I could have brought the wheel in, but just in the camera, it doesn't really work. So I did post some videos, clips of people basically setting up and doing the gyroscope. So what do we want to do? What's the idea here? So when we say what is a gyroscope anyway? How do we define it? So what we'll do is we'll set up the situation of the problem that we saw in the video with the bicycle wheel, basically spinning attached to some rope. So here we have a piece of rope that's coming from the ceiling. So this direction is down. And attached to the rope, we have some axle, a rod, if you will, like this. And attached to the axle is the bicycle wheel. So I'm going to sketch the bicycle wheel kind of lightly because the details of the wheel are not that important. Just the fact that it's kind of spinning is important. Okay, and we'll have it, in this case, spinning around so that it is basically, if we were looking at it from this side, it would be going in the counterclockwise direction. So if the wheel is spinning around like this, and is spinning as seen in the clockwise direction, what we'll do is we'll use the right-hand rule. We'll curl our fingers in the direction, which is now basically the top of the wheel is coming towards you and the bottom of the wheel is going away from you. So we have an angular momentum vector that's basically pointing out like this. So that's L. And its magnitude is, basically it can be represented as some rotational inertia associated with the wheel. So we'll worry about what that is at some other time. But for now, let's just call it I times little omega, which is how fast the wheel is spinning around. So that's the setup. Okay. So how do we tackle this? Well, so what we're going to do is we're going to use the technique that we've used with all of the other rotational problems where we've got things. We'll start with a simple free body diagram. So let's do that. So the free body diagram couldn't be easier. So this is the free body diagram of the gyroscope. So what is the gyroscope? The gyroscope is this whole thing, right? It's the axle and the wheel, all of these things that are attached to the end of the rope. So what does that mean? That means we represent that whole object as a point. And what are the forces on that object? Well, there's just two forces, the weight and the tension. And you might say, well, there's got to be a force involved with the spin, blah, blah, blah. But again, the wheel got started. We started the spinning way before. It's been spinning. We start in this situation where the wheel is spinning already. So, and there's nothing in contact with the wheel, except for, again, the usual things. Say consider the border of the system. What's in contact? The only thing in contact with the system is tension. And the only thing that the tension can do is pull. So that's it. That's our free body diagram. And Newton's second law is pretty boring, again, but we can do it. The net force on the system is equal to the mass of the system, which we'll assume is given here, times the acceleration in the y direction, but that's 0. So we just get that the tension minus the weight is equal to 0, or the tension is equal to the weight is equal to mg. So we know what the tension is. Well, that's nice, but what good is that? So that's as far as we can go. What we really want to do is we want to look at the extended free body diagram. So remember the trick for the extended free body diagram, we just draw an outline of the system. Now, here's the thing. I'm just going to draw the axle. I'm not going to worry about drawing the wheel because there's no forces being applied to the wheel per se. I just need to figure out where these two forces happen to be applied. And that's not hard. The weight force can be applied here. We'll do this in yellow. The weight force is applied at the center of mass. So somewhere around there, don't know exactly where. And, but it's some location. And the tension force in the meantime is applied at the end. So that's the tension force. So the only thing missing from this extended free body diagram now that's critical is the pivot point. So I have to define a pivot point. So I will define the pivot point. Now, again, you may say, well, Mr. Cobalt, the wheel is spinning about its center of mass. That's true. And in all the other problems that we've done so far, we chose a pivot point at on the axle at the center of mass point, which we could do. But we haven't drawn, in this case, we're not looking at the axle, we're not looking at the system like down this path. We're looking at the system kind of off to the side. And furthermore, any point along this axle corresponds to along the axis of rotation, and I'm free to pick any pivot point I want. So to tackle the gyroscope, I will pick the pivot point here at the location where the tension force is being applied. And then you may say, well, why have you chosen that? Well, the reason I've chosen that is that once I choose that pivot point, I can then apply Newton's second law for rotation to see what we get. So Newton's second law for rotation says that the net torque is equal to, well, let's work out what the let's not worry about this side. Let's just figure out what's going on with the net torque. What is the net torque? Because I've just figured out on this side. So again, usually I put an I alpha here, but before we jump to that, let's actually figure out what the net torque is. So the net torque is equal to the torque due to the tension plus the torque due to the weight. But again, our definition of torque, so let me write our definition of torque down so we have it. T is equal to, let's actually write it in the full glorious vector form. So tau sub f is equal to R cross F. So that means that the magnitude of tau is equal to R times F times sine of phi, where phi is. So this is our definition of torque. So by definition, if I say what's the distance, if I choose the pivot point at the tension, this goes to 0. And so therefore this is just this distance here, which that's R. So we'll just call that R. We'll actually say it's a given parameter in this problem. So that's just going to be whatever that. So this is now just R times the magnitude of the weight. Well, that's just mg. Times the sine of phi. Well, phi in this case is 90 degrees. So sine of phi is just 1. So that is the magnitude of the net torque. The net torque has a magnitude of Rmg. That's nice. But more importantly, which way does it point? This is what's critical. Because in every problem that we've done up to now, the torque and the rotation are lined up together, which is to say the torque basically either speeds up or slows down the rotation that's already here. But in this case, what is the direction of the torque? The torque goes R, where R goes from the pivot point to where the force is. So the torque due to weight, let's do the right-hand rule. So I'm going to do the limp listed right-hand rule. Do along with me if you want. So we take our arm and we throw it in the direction of R. And then we turn our wrist so that we can flip our fingers from R to F, right? So this is, again, this force here, that's the weight force. So I'm going from R to F. So that means that the torque is into the board, right? So the torque points into the board. The torque is into the board. It's pointing into the board. So why is that important? That's important in the gyroscope because the torque is pointed in a direction that's perpendicular to the rotation, which is, so the torque is in the board, but the rotation is along this direction here. All right, what does that mean? Why do we care? How does that work? Well, in order for us to tackle it, now that we know which way the torque is, it's into the page, which is to say like this, let's redraw the system, but now as seen from above. And we want to do this because the three-dimensional nature of the gyroscope becomes important in order for us to see the relationship directly. It's kind of hard to draw a vector that points into the board when I'm drawing it on the board. So instead, I'm going to change my perspective. So now we have a bird's eye view. We're looking from above. So, and again, I'm going to sort of simplify things. I'm just going to draw the rod. So again, I'm ignoring the wheel spinning, but I'm just interested in the rod. Now, since I'm looking at it from above, imagine looking down that string. So this is the string, and that's the pivot point there still. And the vector that corresponds to angular momentum still points in this direction, which is to say off to the right. I'm just looking at it from above. So this is the vector that corresponds to angular momentum. But the vector that corresponds to the torque, well, this was into the page, so that means now I'm looking from above. If this is basically, you looking at it before, now the into the page basically corresponds to a vector that points this way. So that's the net torque on the system. So the key issue is that the net torque on the system is perpendicular to the angular momentum. So why is that important? It's important because in the gyroscope, what the torque does is instead of speeding the gyroscope up or slowing it down, it changes the angular momentum. So let's see how we can figure that out. It's completely analogous to what we did before with the uniform circular motion. So let's see. So just to remind you, remember when we did Newton's second law, so this is just a side going back a little bit to linear motion. So we did Newton's second law. We said that F net is equal to MA. And then we rewrote it in a slightly different way. We said, okay, well, this thing is just equal to the time derivative of the velocity. And if you take the mass and you put that in, that's the same thing. F net, that's the same thing as the time derivative of the momentum. So this is an alternate way of writing Newton's second law. That the net force is equal to the linear momentum. And in the case of uniform circular motion, so I'm just going back to uniform circular motion for a second. If I have a particle that's traveling on a path, and that particle has, what's going on there? That particle has a momentum in this direction, and a force on it in that direction. That's the net force. So in this case, that force changes the angular momentum. But because the force is perpendicular to the linear momentum, this force, the centripetal force, doesn't speed up the particle, it doesn't slow it down, it just changes its direction. In other words, as the particle goes around, P just changes direction. It doesn't get bigger, it doesn't get smaller, its magnitude stays the same, but its heading changes. By analogy, here we have angular momentum, annoyingly called L, and torque, and there's the analogous relationship. So I'm going to just erase this and redo it now, but for translational instead of rotational. So we say Newton's second law for rotations. Now we finally do it. We could say that tau is equal to I alpha. Well, that's just alpha. That's just that's just the net torque. Sorry, this should be net. So that means the net torque is just equal to, well, again, we'll just take the rewrite this as I c omega dt, which we can just bring the I in there. So that's just the time derivative d dt of I omega. So in other words, a perfectly equivalent way to write Newton's second law for rotations is tau net is equal to the time derivative of the angular momentum. So this again is Newton's second law for rotations, just rewritten. So instead of force equals the time derivative of the linear momentum, I've got torque equals the time derivative of the angular momentum. This is the critical question. And in the case of the gyroscope, so I've got this equation here. Let me just actually rewrite it so let's actually see what's going on with the gyroscope. In the gyroscope, the torque is perpendicular to the angular momentum. So let's actually draw that situation out. So again, I got the pivot point here, and I've got the angular momentum here, L, and I've got the torque perpendicular. So what the torque is doing is just like in the case of uniform circular motion, the torque is basically applied perpendicular. So this basically corresponds to the change in the angular momentum in this direction, right? Which is to say, as from looking above, the axis of rotation of the system basically changes. It goes from, because it doesn't get longer, it doesn't get smaller, it changes direction. It basically goes from here to here. So in other words, it shifts in some distance here. It goes basically, L moves, as seen from above, it precesses from here to here. So we call this rotation of the axis of the gyroscope, like this, in the horizontal plane as seen from above, that's called precession, gyroscopic precession. In other words, based on everything that we set up, we see that the effect of the torque is not to flip the wheel down. It's not to speed the wheel up or down. It's to cause the axis of rotation to shift in the horizontal plane. We can actually calculate quite straightforwardly what that shift is by using this equation here. So I'm going to erase this part right here just so I can do the calculation. So what I'm going to do the calculations, I'm going to define some quantities. So this little angle, as seen from above, so this is a technique which I call the skinny triangle. It's just a kind of a calculus and trigonometry trick. So this little angle here, I'm not going to call that theta, I'm going to call that d capital theta. So I want to distinguish the angle that has to do with the spinning of the wheel with the angle corresponding to the heading of the axle. All right, so that's the axle right there. And then this here basically is the magnitude of this little shift in change here. So I can basically just use trigonometry in this case, and I can say that d capital theta is equal to, well, that's just the sign, that little bit there, that's a right, in the limit that this is a long skinny triangle, this thing here is just a right angle, right? It's not perfectly a right angle because it's spinning around, but at least for small dl, that's a right angle. So that's just going to be the length L times the sine. Oops, I've messed up. I did it backwards. Sorry. Let me try again. That's wrong. I want to know what this length is. I don't want to know what the angle is. I want the dl, that's equal to the length times the sine of d capital theta. That makes sense. And then the limit that this angle is small, which it is because I've called this an infinitesimal thing, dl is just equal to L times sine of d theta. Sorry, I can't. My brain is just jumping ahead one step. L sine of a small angle is just approximately the small angle. So this becomes L d theta, capital. And then I take this equation, I just put dt under it. Okay, this thing here, I call the rate at which the thing precesses. So we call this capital omega. And this thing here is, I've already argued, that's the torque. So I can just rewrite this equation in terms of capital omega. So let me rewrite it. Finally. So capital omega is equal to, well, that's just the torque over L. So tau over L. This here is the definition of this is the fundamental result of a gyroscope. That the gyroscope is a system that precesses where the torque and the angular momentum are perpendicular to each other at a rate that's simply the ratio of the torque over the angular momentum. Which in this case, well, we already worked out the torque, that's just mgr, and the angular momentum is just I omega, okay? If you want to plug in different values for I, depending on a bicycle wheel or a disc or whatever, you'll get different things. So again, this is known as precession frequency, precession angular frequency. Basically tells you how fast the gyroscope precesses. So notice something, the faster the wheel is spinning, the slower it will precess. If it's really moving, it precesses quite slowly. So cool. So now then, here's the thing. Usually when I go through this exercise, students say, okay, that all seems to make sense, but why doesn't the wheel just fall over? Why doesn't the gyroscope just fall down? And the answer is sort of the same answer to the question of, if you're driving a truck and somebody pushes on the truck and sideways, why doesn't the truck suddenly go sideways? It doesn't, because it's still going forward. And even if you're applying a force perpendicular, that force slowly turns the truck in the same way, even if we're applying a torque, the wheel doesn't just slip down, it slowly precesses. Now there is a cheat here. There's a small cheat. And the small cheat is that when the wheel flips over, if omega was just 0 and you just let go of the wheel, it would flip over. In this case, it's rotating like this, not spinning like this, with the angular momentum this way. So everything we're saying here, this whole analysis assumes that the angular momentum is dominated by the spin. In other words, it assumes that omega is large enough so that the rate of change of the torque is small compared to the value of omega on any time scale that's important to the problem, like the period of rotation. In that limit, this all works perfectly fine. As the wheel gets slower and slower, if this thing gets smaller and smaller, then the contribution of the rotation, again, you think about it, the wheel is spinning this way, but it's also turning like this. So there's two rotations, one very slow and one very fast. If the fast rotation doesn't stay fast compared to the slow rotation, and notice that the slower the fast one gets, the faster the slow one gets, in that limit, this all breaks down and the wheel falls over. But as long as omega is large, enough so that this becomes small for all of these factors, then you're good. This is how a gyroscope works. Any questions about that? So when you talk to somebody, next time you interact with somebody and they say, what did you learn in your physics class over the summer? You can say, well, at least I can understand how a gyroscope works. Okay. Questions? By the way, this whole analysis is done in one of the practice homework problems that I posted. I will emphasize that the practice homework problems are just that. They are just for practice. They don't count for any credit, and they're just a chance to do a few more of these last problems. All right. So one last topic of the day, I think. We'll get this done, and then we'll call it a day. A simple harmonic oscillator. I know that you've already seen a little bit of this in the laboratory exercise, but let's figure out where this comes from. So it's basically an idea. I've got a wall here. I set up a canonical problem. I've got a wall. I've got a floor with no friction. That's supposed to be perfectly flat. Sorry. Horizontal floor. No friction. I've got a spring. So here's my spring. Spring has a spring constant K, and I attach it to a block of mass M. And I measure the position of the block. In this case, we could, for example, define the position of the block as its coordinate corresponding to the center of mass, relative to some relaxed position of the spring. So when the spring is relaxed, this position corresponds to 0, and the spring itself is stretched. So here I'm going to stretch the spring, and I'll highlight that coordinate of stretching as the coordinate x. So if I take the block was here, and it was relaxed, and nothing would happen. I take the block, and I push it there, and then I release it. And I ask, what happens? So I release. And we have the expression of Hooke's law, which tells us what the spring force is. The spring force, SPRF, is a force whose magnitude is K times X, absolute value of X, technically. Well, here I've got positive X, so I won't worry about it too much. So we'll say Kx, and it points in the opposite direction. So the spring force itself points this way. That's the direction of the spring force. So I do a free body diagram. Usual story. I got forces. There's these vertical forces don't matter. They're just weight and things. The only force that matters is the spring force. And normally I would define a coordinate system that's aligned with the direction of acceleration. That's the rule of thumb. But unfortunately here, well, fortunately it turns out, I've already defined x as positive to the right. So I don't have a choice. I just got to pick that there. So then we do Newton's second law. So I'm just going through the exercises, seeing what the consequences of this are. We say Newton's second law, the net force in the x direction is equal to max. So we don't know what ax is, but we do know what the force is. That's just the spring force. So that's the spring force, but it's in the minus direction, so I put the minus there. It's equal to max. So minus kx equals sub ax. All right. You say, well, what do I do with that? So, well, it's a little tricky because a will depend on x, but x is going to change as a starts to accelerate it. Let's just rewrite this. Let's just take the same equation, and what we'll do is we'll bring everything on this side. So we'll say max plus. So we'll bring everything on the same side. Max plus kx equals 0. And then we'll divide by m, and we'll write this derivative explicitly, which is to say we'll say d squared x dt squared. So again, this is a time derivative. D squared x dt squared plus k over m x. So here we have this is equal to 0. I'm going to put a box around it. That's not my answer because all I've done is taken the second law and rewritten it. But I've written it in a special form, a form that we've basically gone from a form that physicists like to a form that mathematicians like. Mathematicians see this and they call this an equation of motion. It's an equation of motion. What does it mean? It means it's an equation that basically governs the evolution of the position as a function of time. In other words, this equation must be true as this object basically moves. It's true at release, but it's also true anywhere else because the acceleration, which is the change of rate of its velocity, is just going to be equal to this value here times this constant here. So I've got an x here, I've got a derivative here, I've got an x here, and then I've got this thing called an equation of motion. And the question is, what is the solution to the change to this equation of motion? Solve. How do we find the solutions? That's the question. So now I've turned this problem in from a Newton's law problem to a problem of finding a solution to a particular kind of equation. By the way, if you've taken a math class, what kind of equation is this? What do we call this? Anybody? What kind of equation is this? What's the name of this equation? How do we label it?
Differential.
It's a differential equation, yes. In fact, it's an ordinary differential equation essentially with a to second order ordinary differential equation. How do we solve second order ordinary differential equations? What's the technique? Anybody? Okay, so I don't expect a technique, but I will tell you. So mathematically, there's several techniques to tackle this problem, and all of them are essentially the same technique, but in different forms. And in physics, I like to be honest about what we're doing. Basically, the solution to solve, we guess the solution. We guess the solution, and then we prove it right. Right? In other words, I don't know any method of just staring at equation, doing what you would call reductionist algebra on it, or applying a set of standard calculus techniques to find the value of x. A better technique, the only technique that I know that works reliably, which is again the same as the mathematics techniques, is to stare at this equation and then realize that only certain possibilities exist for the solution to this equation. What are those possibilities? Those possibilities correspond to an expression for x where if I take that second derivative of that expression and I add it to within a factor of that same expression, this term and this term will cancel to get 0 for any value of x. So I've got a function of x plus another function of x, and that function's second derivative has to cancel itself. So I'm looking for functions whose second derivative are the same as those functions to within a negative factor. And you just start thinking, what could those functions be? So they can't be linear, they can't be polynomial, because you take derivatives of polynomials, you don't get the same function. You get a different function. So functions you can take derivatives of that are the same as the original function. Well, the first obvious function that you might think of is the exponential, because you take the derivative of an exponential, you get another exponential. That's good. Now, the problem is this plus sign here, because each time I take a derivative, I get the same, the derivative could be negative, but the second derivative will be positive. And it doesn't work. I need a function when you take the derivative, it goes back to negative. And it turns out the answer is, if you think about it, only the functions that give you the same function within a factor, but with a negative, are the sines and the cosines. And the fun part of mathematics is you can prove those are the only functions. They literally are the only functions whose second derivatives give you the same thing within a factor of a negative. So again, I will guess the solution. I'm going to make an educated guess to the solution to this. The educated guess says that the solution is going to be equal to some factor, which I'll call a, times the sine of something. Again, this is a function of time, so this something I'm going to call omega, plus b times cosine of omega t. Okay? And this works just great as long as omega has a very particular value, and that is, well, I've got to take omega, again, each time I take a derivative, I get an omega out, so I'm going to have an omega squared there, so that means omega squared has to cancel that, so that means omega has to be equal to the square root of k over m. Then it works, because if I take the two derivatives of this, then I get negative a omega sine squared, and I get negative b cosine omega squared, and everything works out great. So I've solved it by guessing, and I've proven the solution. And if that bothers you, don't feel too bad. Just decide it's okay. For 400 years, we've known the answer to this problem, and we can prove it's right. You don't have to come up with it on your own. I just tell you, this is the solution. Now, A and B are totally arbitrary constants that are basically set by the initial conditions. The more they're set by, by when you define t equals 0 and how far you stretch the string. That it's sines and cosines is not that surprising, because, if you think about it, what do sines and cosines do? Sines and cosines are basically oscillations. And that's exactly what we expect to happen. If I take this object and I stretch it in a string, and again, I demonstrate this in the video, I do it vertically instead of, the MIT video does it vertically instead of horizontally. And I just let this go, then this thing basically is going to go back and forth, back and forth, back and forth. Which is to say a sine wave or a cosine wave or some combination of the two. That's a simple harmonic oscillator. So what do I need you to know? I need you to know that if I set up a system where I basically have this setup where the only force that matters is a spring force in terms of the dynamics of motion, and that force basically is a force, any force, it turns out, that's proportional to we need to make it, we'll just make proportion. Any force proportional to x or to the displacement will give the same effect. not just the spring, but lots of other things as well. Then you will get this oscillation effect. And the key thing is that the frequency of the oscillation is determined by the system. In other words, the magnitude, and all of this, all of these A's and B's, but the frequency never changes. Right? Notice that the stiffer the spring, the harder it is to bend the spring, the faster the wave. Notice that the heavier the mass, faster the oscillation. Notice the slower, the heavier the mass, the slower the oscillation. Okay. Questions about that? So what I'm looking for here is familiarity. I'm basically saying, okay, do you recognize what's actually going on when you have a spring and a mass? And can you make your way through the derivation, if you will? It's not really a derivation because we basically didn't derive this. We guessed it and showed that it was true. Okay. Hold on a second. They're making noise outside my window, so I'm going to close the window. Questions about that? So once we have the idea of a harmonic oscillator, we can extend this idea to a concept of a mechanical wave. So again, I've got this beautiful demonstration of a mechanical wave that I could show you if I had a lecture hall that was stretched out for 20 feet, a nice big spring and all this great stuff. It's really nice. But I had instead put a video out of this nice wave machine made out of skewers and jelly beers, whatever they're called. So harmonic wave. Well, let's actually just start with waves in general. Waves, mechanical waves. So for an oscillator, let's put our results for an oscillator over here. For an oscillator, what we have is a system that basically, it's 1B acts as a function of time, right? So notice all that, the oscillator doesn't move, it just bounces back and forth in place. And we get a solution, which is basically equal to, A sine omega t, plus something cosine omega t. So in other words, we have a solution that is an oscillation function of time. So a wave is like an oscillator, but the difference of the oscillator is instead of oscillating just as a function of time, it oscillates as a function of both time and space. So in other words, in general, a wave, so if I describe the wave, a wave would correspond to some function. So for fun, I will define the function as y. Doesn't have to be any, this thing here basically is some displacement. And the displacement can be in any direction, and it doesn't even have to be a physical displacement, it could be an angular displacement. But it's a displacement that's both a function of x and t. So in other words, it basically is moving, it's a function of space and time. And as long as there's basically a set of rules that govern how that wave changes as a function of space and time, then I can basically write down what that wave is, and I can basically talk about it. So the example I want to talk about is a harmonic wave. So the word, by the way, so we've seen harmonic oscillators. Harmonic, that's just physics speak for sines and cosines. All that the word harmonic means is there's some sines and cosines involved. So it's not hard to figure out what a harmonic wave looks like. Harmonic wave is some arbitrary constant, A, times, well, we'll start with just the cosine. That's the best way to do it. Cosine of, well, let's actually get this written out. I'm a little bit crowded here, so let's actually write it. That's displacement, so let's actually write the whole thing. Nice big space, might as well use it. So y of t is equal to A times cosine of omega t. So there's some, just like an oscillator, there's some oscillation as a function of time, but there's also an oscillation as a function of position. minus kx. Okay, so what we need to do that, oh, wait, there's one other thing I'm going to add to this. One more thing, plus c, and this is an arbitrary, so let's actually unpack this. So for a harmonic wave, this thing here is the amplitude. This thing here is the angular frequency, just like a normal oscillator. And this thing here is called the wave number, sometimes also called the spatial frequency. Okay? And finally, this thing here is called the phase. So again, my goal for harmonic waves is not for you to actually derive them or even you know, solve particular problems with them. It's more cultural literacy. You've got to basically recognize what a harmonic wave looks like. And it has these different components. Now, the phase is the most mysterious one. And all that is basically it's an arbitrary function that says you can offset both position and time in any arbitrary way you want. You could, if you do such an offset, you can convert cosines to sines and various different other things. Omega, that's just the angular frequency, the same as the oscillator. So that means if I stick in one place, if I hold this position steady, then the wave will oscillate as a function of time. The wave number, well, this is a little confusing because it's basically a constant. But here's the thing, and let me put this in. Physicists were so bad, we should have dealt with this long ago. This is not the spring constant. This has nothing to do with the spring. For a normal harmonic wave, there's no spring involved, right? So this I don't know why we use K. It's a completely different K. Okay. And it's possible, it's relatively straightforward to, and again, I won't do the derivation for you, but I'll just sort of give you the relationships. Once you've got K, if you can write it this way, but of course, each of these terms is related to other quantities that you could basically measure. So for example, if you wanted to know what the period was, well, again, this is the angular frequency. So the linear frequency is just 2 pi, and the period is just 1 over that times, and the period is just 1 over that. So the period is equal to basically 2 pi over omega. So that's how long that's how long the wave takes to do one oscillation. And this thing here, which is the wavelength, that's basically just how far it is between crests on the wave. That's likewise equal to 2 pi over k. So that's the relationship between periods and wavelength and these quantities omega and k. So this is what a harmonic wave looks like. This is what it looks like in terms of its expression. It's a function. It's a function of space and time. So let's look at just a simple graphical example of this and just sort of think about how we want to think about it. So I'm going to rewrite this equation, but I'm going to draw sort of an imaginary exercise here. So if I have a harmonic wave, in this case, I'll talk about y being a transverse displacement, but it really can be any displacement. So we'll say that's equal to a times cosine omega t minus kx. Turns out the minus sign, you change plus sign and the minus sign, you change the direction of the wave. So I just want to sort of say, how do I draw that? So for example, it's kind of hard to, so here's the thing, it's hard to draw a function of both space and time. So my plan is, let's start by basically, we'll take a snapshot, which is to say we'll freeze t, right? We'll just set it equal to some value. We'll just set it equal to 0. So we take a snapshot of the wave as a function of time. So in this case, y is set at 0. So that means that this is a function of cosine of negative x. So that, in other words, y basically oscillates, and it starts off with, well, if I'm going this way, it doesn't really matter. I get the same thing. It's a symmetric function. So I get, so y again only of x with t frozen basically looks like this. Okay, where this distance here from peak, basically the maximum position of that function, this is A, that's A, this is also the amplitude. And then the separation between the peaks corresponds to wavelength, which again, we've said that the wavelength is equal to 2 pi over this constant K. So that's a freeze frame, it's like a snapshot, okay? Alternately, we could basically freeze our position, which is to say we could basically have a wave going by and we just hold on to our location. We keep X fixed and we watch the wave oscillate as a function of time. So now I'm going to do Y as a function of time with X fixed at 0. And I get essentially the same function. It's just now that I get a function, I'll do it in green. So this again is, now, so this was X, but now this is time. Okay, hold one fixed and let the other move. So I get another, again, another oscillation, right? Now this, again, this distance here is still A, but now the separation between peaks, that's separation in time. So this separation in time here, that corresponds to the period between waves. Okay. So all I'm going to ask you to do with these waves is basically recognize that, you know, if I write the wave, if I can write a wave as a harmonic form, that's basically an extension of an oscillator where instead of just oscillating in time, I'm oscillating in space and time. And you've got all these different parameters that basically come out of this expression for the wave. Questions about that? Cool. All right, so there's only one more thing I want us to do, and I think I barely have time to do it. At least I have time to set it up. I might finish it tomorrow, but let's just see if I can set it up. This has to do with static friction and the constraint on static friction. So let's write in the corner what we know about friction so far. We know that if the friction is kinetic, and I give you a coefficient of kinetic friction mu sub k, that this equation is true. So this is kinetic only. And furthermore, even though we pretend that it's true, it's actually not a law of physics. It's just, I'm going to make this wavy. It's an approximation that we use in physics 121. And how do I put it? F equals ma, that's the law. Conservation of energy, that's the law. The expression for kinetic friction is an approximation that works sometime as long as nothing is too bad, where too bad means you're not moving too fast and none of these forces are very large. And it's only, I would say, when I say approximately, if it's good to within 10%, you're lucky. I mean, it really is a lousy approximation, to be honest. But we use it in this class, okay? We use it for kinetic energy only. In particular, for static friction, I have said, and I repeated several times, that you may not, that this equation, you know, this thing, if you were to write the functional, an analog for static friction, this is not true. Not true. And furthermore, not useful. But we do have something that you'll find in your textbook, and it's hiding there waiting to bite you, and that is that the static friction is less than or equal to some coefficient mu sub s. And again, I've argued that this is mostly useless. You can't use it to calculate the value of the static friction. It's just a constraint. In an arbitrary problem, you cannot assume that the static friction has this value. In fact, in most problems, it doesn't. So again, unless you know that you're at the boundary between of this constraint, unless you know that, this is mostly useless. So how do I deal with this? What good is this? Well, the good is it basically, let's again, this is a constraint. lets me basically translate constraints on various different problems. So there's basically a recipe for basically using this constraint. If I have a constraint, what's the recipe? The recipe is 1, start by assuming static friction. 2, solve for F and N. 3, using, again, how do I solve it? Using Newton's second law. 3, apply this thing, Fs less than or equal to mu sum n. Okay, to constraint. So here's the key. You don't use this equation to solve for the static friction. You use Newton's second law to solve for the friction. And then you apply the constraint to figure out what's constrained. So let's do a simple example of this. So the example is this. I got a ramp, and I got a box, mass M, okay? So given M and mu sub s, find the maximum value of theta so that the block M stays put. Okay, it's easy to demonstrate that problem. Here I've got to demonstrate it this way. Yeah, that's right. Here I've got an eraser that's sitting on top of another eraser. So the lower eraser is my ramp, and this is my block. And if I tip it at some angle, the eraser doesn't move. Static friction. And if I keep increasing the angle, it still doesn't move. And I keep increasing the angle, some angle, it starts to slide. And I want to know, what is that angle? Maximum value of theta. So that's a constraint. I'm not trying to find the force of friction. I'm trying to find the angle. That's when you use this kind of problem. So what's our approach? Well, our approach is to solve this problem that we've actually already solved, which is to assume static friction. So let's do the free body diagram. Let's do it real quick. So we've got the problem here. Let's do this. Let's do this real quick. I'll be sorry for going over just a little bit. So we got a normal force here, weight force here, friction force here. This is my free body diagram. Let's line up the coordinates like this with the tip coordinate system x and y. So we say Newton's second law, f of x, and we'll start with y. F of y equals ma(y). What do I assume? I assume, again, the recipe, which I literally just erased, said assume static. So that means I have 0. So that means I've got n. So I just do the net force in the y direction. So that's n minus w cos theta equals 0. So n equals w cos theta. So n equals mg sine of theta. I'm going to put a kind of curly box around that because I'm not interested in n. I'm interested in theta, but I don't, that's n in terms of theta. And then I do the same thing over here, Newton's second law in the y coordinate. And again, we've solved this problem before, but let's just make sure we get the right answer. So, sorry, in the x coordinate. So we say f of x equals max. And again, start assuming that it stays put. So you set that equal to 0. So then you get, w sine theta minus f. This is my force of static friction, equals 0. So I get then F equals mg sine of theta. So again, I've used the problem to find n and f. And then once I have n and f together, then And only then, once I've solved for them, do I apply the constraint. So now I apply the constraint. Again, mostly useless, only if I'm interested in constraining a value. So I say f sub s is less than or equal to mu sub s. Again, mu sub s will have to be a given, times n. So I just plug in the things I've already figured out. So this will be mg sine theta is less than or equal to mu sub s times mg cos theta. See what I've done? I haven't solved for these things. I've used my previous solutions and plugged them in. And now I just do some algebra. So cross out m. Now this is important. This is an inequality. So if I divide by a quantity, what do I have to make sure of? I have to make sure that the quantities I'm dividing are all positive. Because if I divide by a negative number, it changes the sign of the equality. So when you're doing the algebra with inequalities, you have to be careful. Every time you cross something out, you have to make sure it's not zero and not negative. Cross that out. Cross that out. As long as theta is positive, cosine and not greater than 90 degrees, happily, these things make sense. So basically, I can bring the theta on this side. So I can say sine of theta over cosine theta less than or equal to mu sub s. Or, in simple words, the tangent of theta must be less than or equal to mu sub s, which is to say theta itself must be less than or equal to the arc tangent of mu sub s. That's my constraint. In other words, I get it. In other words, the answer to the question, what is the maximum, is this constraint is true. So the maximum value is right at the border where this constraint goes from being true to untrue. It must be true that the maximum value is the arctangent of theta. I like to do the algebra with the inequality in it, because that way I can keep track of what's big and what's small, what the constraint is. This constraint says that theta cannot be larger. It must be that value or smaller. That's the constraint. So the constraint is only useful, this equation is only useful when you're interested in the transition between static and kinetic friction. It's only useful at the limit where static friction is about to let go. And it's not otherwise useful any other place. And even then, it's not useful for calculating the value of the friction. The only way to calculate the friction is to apply Newton's second law. That's the only way you can apply the friction. The only thing it's good for is to figure out constraints on the parameters that you haven't already defined. Okay, so that's all we have for static friction. Whew, now we're done. Sorry, I ran a little bit over today. Anybody have any questions about this? Anybody have any questions about the homework that's due? Anybody have any questions about anything else having to do with their life and this class? We're almost done. Just to point out while you're thinking, I've posted a practice homework. The solutions are already with the homework. I've also posted, will post solutions to today's homework and a practice final exam later this evening, I guess it will be. So everything you need for the whole semester will be posted by sometime tonight. I'm often asked this question: what will be on the final exam? So I'll talk about it tomorrow and I'll talk about it Wednesday, but I'll say it each of these 3 times. This is what will be on the final exam. Everything up to and including the homework that you're turning in today, in other words, rotations, except for gyroscope. Of the 6 problems, 5 of them, that's all you'll have to know. In other words, at least, maybe even, and again, a constraint. At most, I will have 1 problem on the final exam that covers material that we'll do this week. So at most, 1 problem on the final exam that has to do with either gyroscopes or waves and oscillators, or what we'll do tomorrow, which is non-inertial reference frames. So at most, 1 problem on those 3 things. And the other 5 problems will be on everything else that you've already covered, all the way up through rotations and angular momentum. So if you want to know the answer to the question of what do I need to study, the answer is if you study the stuff you've already done, as opposed to the stuff we're doing this week, you've got 5 out of 6 of the problems covered for sure. It could be more. It could be 6 out of 6. I'm not promising to put a problem on the stuff we're doing this week, but I might put at most one problem. Okay. Now you know it's on the exam. I mean, conceptually. But we'll talk about it again tomorrow and Wednesday. Any other questions? Going once, going twice. Don't use this equation. So again, don't use this equation unless I'm asking for constraint. The word maximum, minimum, that's usually what we're talking about. Otherwise, it's useless. All right. So nobody has any questions? Again, I'll have office hours today at 5:30. And if you need to talk to me before then, just send me an email. I'll be happy to meet with you. And otherwise, tomorrow we will change things a bit. We will go from physics of the hundreds of years ago to physics of the 20th century, at least a little bit. All right, talk to you soon.